Right, let's start. So yeah, we have to be clear about our term project plan. So initially, I included the term project as part of our evaluation criteria, and it's still holding true, but I thought that some students may have no idea about what to do about the project, and then I figured I don't want those students who have no idea to forcefully do something related to this class other than your main job from your lab and your research. And so I'll provide another alternative where you can submit some homework that I give you. Okay, so that homework will be mainly about, it's not restricted, but it will definitely include what we currently study about this EM algorithm and Gaussian mixture, and maybe implementing the Gaussian mixture model, and then test or run your own algorithm for some sample data. And also, it's not just a implementation, but that homework will also involve some derivations or mathematical proof about this EM algorithm and their application in Gaussian mixture model. And I'm still preparing for it, and so it will be it will be ready until before the next class, I think. And then you can submit it by around the end of the semester, okay? Probably before the final exam week, okay? But if you have your own ideas and about your project, and then you can just go ahead with that. And then in that case, you can just skip the homework or this kind of a little bit in-depth kind of homework stuff. Okay, so you can just ignore that and then focus on your own project. Okay, and it's just a free topic, so you can also form up a team of 2 or 3 people, and then as a final outcome or the material to submit will include your code and also your paper-like report. Maybe you can select some template from some major conferences in the CS, and so based on that template, you will have to submit your project report based on LaTeX, okay, not just a Word or Area Hangar. Okay, so I just only allow the LaTeX, and then you can use an overleaf and other your local LaTeX compiler and editor, and I personally use Lix, and this is quite convenient LaTeX editor that can lower the learning curve. And but this is the only drawback of this Lix as a LaTeX editor is it's not cloud-based. So we cannot edit a single document simultaneously over the cloud environment. So this is the only drawback. But at some point, I hope some other geniuses are implementing or offering this cloud-based Lix editor, because it's so awesome. But anyways, you will have to write your project report, in the form of this LaTeX compiled PDF. And also, so for your homework as well, you will have to submit your homework answer sheet and your maybe experimental result by using some sample data. And I ask you to submit it in the form of a LaTeX files or LaTeX compiled PDFs. Any questions? 평가요? 글쎄요. 잘해야죠. So the evaluation is inevitably involving some subjectivity because it's a free topic. I mean, the term project, even if you choose this term project, it's just based on your own choice of topics. So it's already kind of subjective in terms of its evaluation. And also these are homeworks, and I mean, I will make it as much interesting as possible, and also as much challenging as possible. So I will not make it kind of trivial, so that those people select or choosing this homework option may get kind of better credits unfairly. So I will avoid this kind of situation. Any other questions? Right? And then last time, I tried to explain EM algorithm from scratch, but I realized that it's quite difficult because I myself didn't ingest or digest or fully understand this EM algorithm to my heart. Okay, so I try to follow this material, which I found to be quite useful, and this one is CS2219 lecture note, and I believe this lecture was originally given by Andrew Ng, who actually did a professorship in Stanford, and we know his well-known class offered in Coursera machine learning course, right? But that is a really entry-level course from this course, CS2219, which is about, I think it's mainly about the machine learning, but it's much more theoretically or mathematically deep. Right? So I'll try to follow this material a little bit during our class, but not all of them. And in case of choosing this homework option, and then I will ask you to review these proofs and derivations, and also ask you to give a kind of a detailed justification between each steps of derivations, and some of those that are omitted in this class materials. Okay. Right. So. So at a high level, this EM algorithm, or just to motivate you guys, if you heard about like variational autoencoder. So in the case of variational autoencoder, the main derivation to obtain this variational autoencoder formula criteria and optimization algorithm is not Elmo, but elbow. I forgot the acronym. Someone can tell me what the acronym is? Lower bound. 네? 뭐였죠 이게? 에비던스? 에비던스 뭐라고요? 에비던스 로어 바운드? 끝이요? 뭐가 안 맞는데? 이게 에비던스 로어 바운드, 이거 바운드? 여기서 이거? 에비던스 로어 바운드. 역시 잘 모르겠네요. 이 의미를 아는 사람 있나요? 직관적인 의미. 하여튼 에비던스에 의해서 로어 바운드를 구하고 그걸 올리자. Okay. Right, so this is a main kind of idea to optimize this variation autoencoder architecture. And this elbow and also this EM algorithm, yeah, although I don't have a kind of full and in-depth understanding about it, but those two are really closely related in a sense that they are setting the lower bound and then maximize this lower bound iteratively. And both of, yeah, the underlying technique or trick behind these two algorithms is called this Jensen's inequality. So this is so important one. And so suppose f is a convex function like this. Okay, so this is one example of a convex function, and suppose your x, which is a input value to our function f, which is a convex. Okay, and this is now a random variable. Okay, random variable, and then random variable means x can be having some of different values of a and b and so on, but with a different probability, right? So x being equal to a, suppose that is like 70% probability, and x being b is like 30% probability. If we have this associated probability table, and then we can call it as just a random variable, right? Right, and then we can think of this e of an x, or an expectation of an x. Okay, so in this case it is like x times p of an x and summing it over all the possible x, right? So this is the definition of e of an x, right? But intuitively this x times p of an x and its a summation will be just an interpolation. I think I mentioned it or discussed it. Yeah, when discussing like convex combination and convex whole and convex set and so on, right? So in this case, yeah, it is like suppose a is maybe 2 and 5, and it is like we have 2 and 5 over here, and 70% and 30%, and then is expectation of 0.7 times 2 plus 0.3 times 5 is somewhere around here, right? So in this sense, it is just an interpolation between the 2 points. So if we consider this internal region, and then the expectation will be somewhere in this internal region. And if it is a vector, so if x is a vector, and then we can do the same thing, right? And then maybe x is a two-dimensional vector for this random variable x, and 1, 1 and 3, 2, and maybe 2, 4. Okay. And then we understood that this is a convex hull formed by these 3 vectors, right? And then suppose our two-dimensional random variable of 1, 1 and 3, 2 and 2, 4. Suppose our two-dimensional random variable can have only these 3 possible choices or 3 possible vectors, and the probability table is 0.1, 0.2, 0.7. Okay, suppose, let's imagine this kind of probability table associated with this two-dimensional random variable. Okay, in this case, what is the expectation of x, where x is these two-dimensional value, right? Two-dimensional vector. So in this case, it is like so this is a, b, and c, a, b, and c. So it should be close to c. Something like this. Okay. So similar to this interpolation, where we have like 3, 3, 2, 7, Okay, so I think it is 1 over 7, 1 over 1, and 2 over 1. Okay, so this probability, I mean, inversely proportional to this probability, I mean, this interpolation point will have a closer distance to that higher weighted point. Okay, but still in this sense, this guy is an internal point, right, or interior of this convex hole of these three extreme points. Okay, so in this sense, it can be viewed as this kind of interpolation in the same manner. Okay, and in the case of a convex function, okay, convex function, and also this is still a convex combination. Okay, in that sense, it is called the it can be viewed as an interpolation, and this is also interpolation and also convex combination as well. So basically, expectation is convex combination, which is kind of somewhere in the middle of these extreme points, right? And in the case of convex function, it has the property of like, if we have two extreme points, and then if we choose any internal point over here, and so on, and there, so we first to perform the convex combination using these two, and then probably like this guy is a 70% and 30%, right? And then we can first perform this convex combination and then compute there, obtain the function value, okay? And then this function value is always lower than, we just perform the convex combination of function value itself, okay? So in this case, let's see. So what's the meaning of this value? So it is still the interpolation between these two function output, okay? So if you remember, or if you're familiar with the linear algebra, and then we have a similar kind of property. So linear algebra, in the linear algebra, the linear transformation has the following property. Right? So in this case, we obtain the linear combination of an x and y first, and then obtain the function value. And then it is the same as the result of the linear combination of the function value itself first. Okay? So if we obtain this relationship for any a, b, and x and y, and then this function is linear. Okay? And then if the function f is convex, okay, and then it is changed into this form. So a plus b should, because, so so in order to define the internal point between the 2 points, so we restrict our linear combination into a convex combination, okay, and then we can consider these two cases of computing the function values. First, performing the convex combination, and then obtaining the function value, and then first obtaining the function value, and then performing the convex combination. So in this case, if the function is convex, and then it has this relationship. Okay, so that means like the right hand side is like interpolating between the y points, y values, and then the left hand side is interpolating first between the x values, and then obtain the function value, and then the former or right hand side is always larger or greater than this value. Okay, so if it is satisfied for any a, b that satisfies this, and for any x and y, and then it is called a convex function. Okay, and then if some function is sometimes like this and sometimes like this, it is no longer be called a convex function, right? But if this function satisfies always like this criteria, and then for any of the a, b, and x, y satisfying this, right? So in this case, it is called a concave function. Concave function. Okay. So in the case of convex function, yeah, 네, 이거 한국말로 이거는 아래로 볼록이라고 하고, concave는 이제 위로 볼록이라고 하죠. 그리고 이제 모든 함수가 모든 영역에서 다 위로 볼록하면 이거 concave, 모든 함수, 그 함수가 모든 영역에서 다 아래로 볼록하면 convex라고 부르는 거예요. 그리고 언제는 위로 볼록, 언제는 아래로 볼록하면 그거는 이제 convex 혹은 concave function이라고 부르지 않고요. Right? So we now understood the convex function and the concave function, or none of them. Okay? And yeah, so this is a kind of a Jensen's inequality. So Jensen's inequality is, so we kind of studied this Jensen's inequality in a kind of reversed order, but by definition the convex is like the second derivative is strictly positive, or it is zero at a discrete point. But anyways, if it is satisfying, if it satisfies this, and then it will satisfy this. Okay. All right. And so using this, we can relate this guy with the notion of the expectation, because expectation is basically the convex combination of an x, right? Because all the probabilities are positive or non-negative, and their sum is equal to 1, and thus their weighted sum of an x with respect to the coefficient satisfying this is called, it can be viewed as convex combination. Okay. Okay. Then from here, this guy, f of an x. So this is like, so x is like 2 and 5, and we know p of an x has 0.7 and 0.3, and let's think of f of an x. And here 2, no, here is 2, and this is maybe 8, and maybe this guy is 4. Okay, so E of expectation of an fx, f of an x. So this is fx times p of an x. So this is the definition of an expectation, right? And so, like in this case, 8 times 0.7 plus 4 times 0.3, right? In this sense, it is an interpolation between the y values. Okay, so this is the interpolation between the y values. And then what about this? E of x, and then f of an e of an x. So we first perform this expectation of an x, right? So in this case, like 0.7 times 3 plus 0.3 times 5. It was 2, right? Because it is 2 and it is 5, right? And then it will be around here, and then we obtain the function value later on, and then we will have this guy, right? So if the function f is convex, E of f of an x is greater than or equal to E of, no, f of E of x, right? So this is Jensen's inequality. Okay, so that's how we obtain this. And then now let's move to this EM. So we have this observed variable typically obtained from independent and identically distributed density, okay, for each of these x1 through xm, right? And then this is the log likelihood of, yeah, so this is our probability with respect to some particular parameter theta, right? And then our IID sampled observations from x1 through xm will be the product of this guy, right? So this is the joint likelihood of observing our particular x1 through xm when given our probability distributions are parameterized with the data, right? Okay, so if you are, if it is a little bit abstract, and then you can imagine, right, our Gaussian mixture model example. What was our Gaussian mixture model? So our Gaussian mixture model was, we first sample some multinomial distribution. So let's call that as Z. As Z is, yeah, multinomial distribution, right? So if C is, I mean, their sample space is 1, 2, 3, having three different components, okay? And then this one will have some parameter values, 0.2 and 0.7 and 0.1, okay? Their parameters are summing up to 1, right? And then we first sample Z, right? As one of these 1, 2, 3, and then for each of them we have the first Gaussian x when Z is 1, okay? So this guy is following some Gaussian of mu1 and some sigma 1, and x when Z is equal to 2, and then it will also follow another Gaussian that is parameterized by a different one, okay? So we have an x3 as well, right? Okay, so what are theta? So theta are those values and also these values, okay? And then given, yeah, parameterized by these theta, we want to obtain, we want to maximize this likelihood, and then we want to find out such a theta that will maximize this likelihood. And then in detail, if we have a m number of IID samples, and then this likelihood can be represented as a product of these, yeah, each likelihood function, okay? And then if we consider the log likelihood, I mean maximizing this, and then maximizing, I mean the argmax of this guy with respect to theta will be the argmax of log of this, right? Because log is a monotonically increasing function, right? So if theta was maximizing this, and then theta will also maximize the log of it, okay? Okay, so we will use this log likelihood, and then it will be represented in this form. So here we have a typo over here. So log of the product will be the sum of log of each term, right? So we now understand this guy is the log likelihood. So far so good? Okay, and then here, yeah, we also have a random variable Z, which is not observed yet, right? And so we can first think of this complete likelihood or joint likelihood of X and Z, or more exactly, this can be viewed as like this. So So this X is involving entire set of observations that we have, right? And then what about Z? So how many Z do we have? So we will also have M number of Z, and they are independent with each other, right? So for each of them, for each sample, we first independently obtain Z first, and then obtain X, okay? And then if we have an M samples, and then we will also have an independent Z random variable Z, right? So we can think of these joint likelihood, right? But still, this guy, because of this independent, statistical independence, it can also be viewed as like this times right? Okay, and then we need this guy, right? But we first have to think of their complete likelihood function involving both of X and Z. And then how can we obtain this guy? P of an X of an 1 parameterized by theta, okay, from this joint likelihood. So the joint likelihood, so yeah, suppose we are given this joint likelihood, and then how can we obtain P of an X? We will just marginalize Y, right? So it's like so in this process, so our probability density function is defined so we already discussed about it, but this suppose this is an X and Z, X and Z, okay? So initially we have this joint likelihood function where the sum of area or volume under this curve is 1, but here how can we obtain P of an X? If this is an X, and then we will just squeeze them along this direction or of Z, and then that's how we obtain this marginal distribution, right? So this is represented in this equation, and thus over here this guy can be represented in this form, P of I, Z of I. So we first have this complete or joint likelihood, and then we just marginalize the out with respect to all Z's, right? So if we have M number of likelihood function that only involves X, because we need a marginal distribution that is not dependent on Z, because we want to obtain the maximum likelihood estimation of theta only with respect to this P of X, right? Because we do not know Z, and so this is original log likelihood function, and so this log likelihood function is also defined as the marginalization of the joint likelihood involving both of these X and Z. Okay, so far so good, right? And then now we can just consider any of this a particular function Q. Okay, so we just introduced some function Q that has an input of Z out of nowhere. So in this case, Qi Z of an I is for I's data item, I mean for each of our data items of x1, x2, and x3 and so on, they are just considered or treated independently, okay? And then for the first one, x1 and z1, z1 like this, okay? So here we can consider some function of z1, okay? So what is the possible values of z1? z1 is, in the case of Gaussian mixture model, z1 is still b1 of 1, 2, and 3, okay? So 1, 2, and 3, and let's suppose, yeah, we just introduced this function out of nowhere, but let's consider this function to satisfy this kind of thing, okay? So f of z1 is still a function where we have an input as 1, 2, 3, and their function value is all positive or non-negative, and their sum is equal to 1. Okay, so in this case, in this sense, we can view this arbitrary function that we additionally introduced, which is an f of z1, as some arbitrary probability distribution of z. Okay, so it just satisfies any arbitrary function where the input is c values and their sum is 1, and also their function values are positive and thus non-negative, and so this can be viewed as some additionally introduced arbitrary distribution, okay, for z. Okay, so that is this qi zi, and the reason why we have this I as a subscript is because we can freely introduce this f for each of our observations. So x1, we can have our own f of z1, and for x2 and for its associated z2, we can also define additional, completely different f of z2. Okay, so in this sense, we have this subscript I over here. Okay, so that is the meaning of this qi of zi, and because we just arbitrarily introduced this guy, we can just divide it by this guy for the original term, right? Right, so here we are now ready to apply the Jensen's inequality, because this one, okay, this one works as a linear convex combination weight, or some kind of an expectation stuff, right? For what? For this measurement, right? And overall, this guy is a kind of an internal point where we have this kind of an extreme point, right? And so it is a convex combination. Up to this guy, it is convex combination, and then this guy, we have a log of it, right? So this log function is having the shape of this. So this guy is a concave function, right? So this is a concave function. Okay, so at a high level, log of something. So we first performed convex combination, just like obtaining like this internal point first, and then obtain the function value or compute the function value or function output, and then let's think of moving this log into this sum. Okay, so this one still works as a convex combination coefficient, and then now we first perform the function output. Okay, so in this case we still perform the convex combination with respect to the same convex combination coefficient, and so this guy is similar to like the computing the interpolation with respect to y values, and this guy is like convex combination first using x value and then obtain the function value, right? But this guy is a convex concave function. The log function is concave function. So which one will be higher? So in this case, it is a convex function. So first performing convex combination will give us lower function value, right? But if it is a concave function, and then if we perform the convex combination first, and then it will give us higher point. Right, so so we have a convex concave function, and thus this guy. Okay, so performing first convex combination and then obtaining the function output will be higher than like yeah, this guy is higher, and then this guy. This guy is something like okay. So over here, for example, right? Does it make sense? Okay, and then starting from our marginal log likelihood function, and then we obtained this lower bound of our log likelihood function that only involves x. Yeah. Without unobserved variable z. Okay, and then now let's look into this part. And by the way, this guy, the sum over all i's, so that can be viewed as, yeah, that can be, yeah, ignored for now, because that is just an independently done, right, for each of our data items that are statistically independent with each other. Okay, so let's focus on this green box. Okay. So in this case of green box, yeah, let's consider some meaning. Okay, this meaning is, so we have this guy, right? So what's the meaning of it? So we have originally this joint likelihood function or joint probability function, and then it is scaled or divided by QIZI. Okay. Okay, so let's also use this guy. So this is an X, and this is a Z, right? And this is this guy, P of X and Z, parameterized by theta, right? And then it is divided by Qi of Zi. And then as I mentioned, we can choose any arbitrary function for this Q of Ci as long as it is satisfying some probability distribution, okay, where all the elements or function values are summing up to 1, and then they are, each of the function values are non-negative. Okay, so suppose x is somewhere around here. Okay, and in this case, what will be our function values? Yeah, what will be our p of x and z when x is fixed over here? And then it is just a sectional image when just cutting them into this part, into this direction. Okay, and then what is our q of z? So q of z can be arbitrarily defined, right? And then we can imagine some other q of z where we have like z is like this kind of shape. So q of z is like where it starts from over here and then monotonically decreasing into this point. Okay, and then what is the ratio between the two, or this one divided by this? Okay, so in this case, so if we have like a relatively higher point, and then at a particular xi, and then this sectional image, and then it is like downscaled further, and then p of zi is having like a small value at this ci, and then this function value is divided by this guy, and then this function will be like gradually gradually higher. Okay, does it make sense? So we can imagine additional function defined on z, and then for each value over here and over here, and then we divide this value by this value, and so on. So that is the meaning of this value. Okay. So the reason why I mentioned that we fixed xi is because xi is really fixed, because xi, x1 and x2 and so on, these are our already given like training data. So x1 is fixed as some known values, x2 is also fixed as some known value, right? So we can consider that known value, and at that particular point we can consider their joint likelihood at that fixed x value. Okay. And then this guy, we know that, this kind of function. Okay, so let me just try to draw this. So from the two-dimensional P of x and z and theta, and then this guy, when suppose x1 is fixed as maybe 3. Okay, so let's say x is a scalar value, and then this joint distribution when x1 is fixed as 3, and then this guy is z, and z will have, suppose z is some continuous random variable and having something like this kind of distribution. Okay, so this is P of x comma z, P of x comma z, where x is fixed as 3, like this. Okay, so let me ask one kind of question. So what is the sum of it? What is the sum of it? Is it 1 or not? It's not, right? So altogether the volume under this curve is 1, right? And we consider this a sectional image where we cut when x is fixed as 3, then we just cut it and then bring this curve into this form. Okay, right? Okay, and then we additionally introduced this q of zi, where it is also defined over here. And then suppose z q of z is something like this. Okay, and still, I mean, in this case, q is like the sum of it is 1, so that we can satisfy, I mean, this q's work as a convex combination coefficient, right? And then how about just dividing this guy by q? Okay, so if it is a 0.1, and then it will be like 10 times higher, right? Because it is divided by a smaller value, and if it is maybe 2, and then this point will become like half, right? We divide this guy by this guy, right? So that is the meaning of this guy, right? And so drawing it, okay, something like this. Okay, so this is a downscaled version of this guy, and then this is our, it can be viewed as function of c, right? And then using this function, and then we compute is expectation. Okay, is expectation with respect to the probability distribution of this guy. Okay, so from here, so this one is a valid probability distribution or probability density function, right? So in this case, so we have some measure that is also dependent on z, and we have some probability density for z. If we just multiply them together and then add them together, and then it can be viewed as like this measure, and is expectation of with respect to z, but which probability distribution this z follows. Does this z follows? This guy is following this guy. Right? So that way, this guy is our function output when given an input input c, and then their corresponding probability density is qi of zi, and then this can be viewed as this expectation when following this guy. Z is following this arbitrarily introduced density function. Okay. Right. So this guy is this green box. Okay. So this green box. Okay. So that is corresponding to this guy is our f of z, and then we compute this so I made one mistake over here. So this guy is not the same as that green box, right? So this guy is so we were discussing about this guy. Right? Okay, so this part can be written in this form as we saw earlier over here. Okay, and then we finally apply the log function. So here this function f is log. Okay, and then now let's think of this guy, the green box over here. Green box over here, and then green box is f of this function. Okay, so this f of z is over here, and then this f is log. Okay, so up to this point, this point is this point, right? And then we finally apply the expectation value of this function outputs, right? So this guy comes from here. So this is a different representation or rewritten version of that inequality. Okay. Then now so the next story, the next step in our story is, so we want to maximize this guy, the log likelihood of our observed variable x, right? And then it has the lower bound of this guy, okay, this lower bound, and we want to maximize this lower bound. Okay, we want to maximize this lower bound in a way that these two is equal to each other. Okay, so this one is somehow fixed. Okay, this one is somehow fixed, but this guy is, this guy can be changing. This guy can change depending on what? So fixing this guy, and this guy is working as a lower bound for our log likelihood, right? But when obtaining this guy, what we did was to introduce some arbitrary function f or q of zi, right? And for any q of zi, this inequality will hold true, right? But if we consider this guy as fixed one, and then how can we make, I mean, yeah, basically depending on q, this part will become smaller or larger depending on different q's, right? So if we q as a certain one, and then this value might be 10, or if we choose a different q's, and then this part may be 9 or 3 and so on, right? So we want to find out the maximum possible lower bound. Okay, so that way we can guarantee that, okay, this guy is at least larger than, for example, 10. Okay, that as what we found as a maximum value, yeah, for this quantity. Okay, so how can we maximize this quantity, or how can we achieve this equality? Okay, so from the perspective of choosing some q. Okay, so previously this inequality holds true for any arbitrary q, but in terms of maximizing this lower bound so that this value and that value is equal to each other, in that case, what will be our q's? What will be our optimal selection or choice of this q? Okay, so q is no longer be arbitrary function, but yeah, q is chosen in a particular manner. But let me just go back to this Jensen's inequality and then point out one important part. So here, how can we achieve this equality for this Jensen's inequality where we have this guy? Okay, so first performing the f of an x, where f is a convex function, and then yeah, compute the expectation with respect to x, right? And then x can have like different values, right? And then obtain this expectation value. And then yeah, I mean, I'm just describe the meaning once again. And then this guy is the interpolation first, and then perform the y values. Okay, so here, what if we want to achieve the equality? In this case, what about this? Yeah, what about this value x are all the same? So rather than x being or having a different value of 3, 2 and 5, what if our x or input value, two different input value x's as the same values? So in this case, we will start with the same value over here, and then its interpolation or convex combination will remain as that same point, and then the function value will be over here, and then also its function value first, and then they will also have the same function value, and their convex combination will be the same, right? So in this Jensen's inequality, if we achieve the equality of this Jensen's inequality, and then what we can do is to make this x values to be the same as each other. Okay, so there is literally only one possible x. Okay, right, so back to this example. So what is our x over here? So the corresponding x is this part or this part, right? So that is our x. So if this value is like different values, and then its corresponding probability values and the weighted sum or weighted average, right? So based on this meaning of this expectation. Okay, so in this case, this inequality will be strictly like the left hand side will be larger than the right hand side. But if this value remains a constant, or this guy that is used as an kind of ingredient or extreme point that forms our convex combination, if these values are in the beginning these values are just the same as each other, and then this equality, this inequality will become inequality. Does it make sense? Okay. So what is this value? So we already discussed about this value. So this value is a scaled version like this, right? So starting with the joint at a particular fixed xi, which is the known value, and then this is a sectional image, and then we consider any arbitrary q, okay, and then we scale down in this manner. So if we just divide this graph at each by its corresponding value defined in our q, okay, and this is our quantity over here, right? And then what is the expectation of it? So this expectation is, so those are our x value, or f of an x, and then multiplied by the q's, right? So these are working as a linear convex combination ways again over here, right? And then we just compute expectation of this value in this manner by using this as probability distribution. Does it make sense? So that's the meaning of this part, right? Right? Okay, and then now now we have to make this part as a constant, right? So that way we can make the Jensen's inequality to be equality, right? So we want to make this part or this graph to be all the same or constant, right? So if we choose some q, some optimal q or some suitable q, and then when dividing it by q, and then this graph or this measurement is just a constant. Okay, so in this case, and then in this case this part will remain just constant, and thus this Jensen's inequality will become equality, right? So again, at a high level, we know that having the equality requires this x should be all the same, right? X should be all the same. Okay, in that case, their internal point or their interpolation or their convex combination will remain just as the same value as it is, and then their convex combination, and then computing the function value, and then their function values, and then convex combination will remain the same, because we are just literally handling the same point, single point, right? And so what is the what plays the role of x over here in our in the Jensen's inequality in our case? Okay, this part is our all the various or all the different x values, and so if this value remains the same or constant, then we can obtain this equality, right? And then what is that corresponding q? Where is that corresponding q? So we have this guy, okay, and then we divide it by some q for each element, and then we obtain the constant value, okay? And then in that case q can be set as just the exact same function like this, right? So if we set this guy as that guy, and then dividing that guy by q, which is the same as the original function, and then it will be just the constant function value. Does it make sense? Okay, and then this guy. Okay, this guy. So let me. It's now ready to. move over here. So this quantity playing a role of an x in our Jensen's inequality, that should remain as constant, right? And then in that case, there's a q, which is a divisor, or for each zi, we divide it by q of zi, and then if we set our q, which was initially like arbitrarily chosen, okay, but now it is chosen as like proportional to this guy, okay. So in this case, so why do we see the proportionality instead of just the equality? So intuitively, you can think of these two green lines over here and over here to be the same as each other, but that guy, that green guy, is not a probability density, because that is not summing up to 1, right? Because that is just a sectional kind of curve or graph from our entire joint distribution, right? So this is a sectional kind of graph where the area under this curve is not necessarily equal to 1, but we need the area under this curve of Q should be equal to 1, right? Because of because they work as a convex combination coefficient, and so we actually bring that in and then scale properly so that the area under this curve to be 1. Okay. And then how can we achieve this Q so that their sum is equal to 1? So we know this guy is proportional to this guy, so that this guy this guy holds true. Okay, and then this Qi can be now defined as this form. So in this case, suppose the area under this curve is only 0.3, okay, and then we just scaled it by the ratio of 1 over 0.3. So we just elevate or increase the height of this graph by 1 over 0.3, right? So that the area becomes now 1. Okay, so this guy is 0.3. So we divide this sectional joint likelihood or joint density by their sectional sum. Okay, so that is our Q. Okay, so in this case, we can satisfy the Jensen's inequality. Any questions so far? Okay, and then now this was our joint density, and this is our sectional sum. Okay, we divide it by that. We divide this function by that, and then what is that? What is this function? So we already saw this kind of process when obtaining the posterior distribution. Okay, so that way we can obtain this Q, optimal Q, that will achieve this equality of Jensen's inequality as this posterior distribution of Z when given X parameterized by data. Does it make sense? Right? And then once we choose Q in this manner as a posterior distribution of Z given X, and then that's when these inequality becomes equality, right? Right, and then our formula in equation 3. Okay, so now due to this equality, our likelihood defined over here is now represented in this form by just plugging in qi as a posterior distribution, and then we just maximize this representation or this expression with respect to theta. Okay, so that is our see. So that is our overview of an EM algorithm. So here at a high level, so we assumed a fixed theta, okay, and fixed theta and fixed x. So x is always fixed, okay, and then in the process of maximizing this lower bound, we chose the optimal choice or optimal option for this q, which is a posterior distribution at a current state. Okay, so that way we obtain this q, and then we just plug in q in that manner, and then we obtain this value, and then from this expression we actually set our theta as a variable, and then we perform this argmax of this representation with respect to theta. So here, when viewing this left-hand side as a fixed quantity, and then theta is also considered as a fixed one, and then now we focused on choosing optimal q's, okay, and then once q is fixed and we plug in q into this form, and then given that form, and then we optimize this representation with respect to our theta. Okay, so that's the second step of this EM algorithm. And then once we update this theta, and then this value is also considered as a fixed one, and then we now update this lower bound by choosing the new q value with respect to differently updated theta. So in that case, we kind of iteratively maximize this lower bound by choosing q's and theta alternatively. Any questions so far? Okay, and then there is a discussion that this algorithm is guaranteeing to some value by just showing this two iterative process of these two steps is monotonically increasing this representation. And then let's look at this remark as well. So we can also view our maximum likelihood estimate of a marginal distribution. So we started from this marginal distribution where this z is marginalized out from this complete likelihood, right? So in this case, this guy or this representation can be viewed as having like two different components where we kind of optimally choose. The first one is theta, of course, which is our parameters. What are our parameters? In the case of Gaussian mixture model, these are our parameters. Okay. And then what are our q over here? Q is the arbitrarily chosen distribution, that the additional distribution of z that we can choose arbitrarily, right? So we can view our objective function as having these two variables, Okay, and so here at the one step or the first step, we choose this optimal Q. Okay, that will maximize our marginal likelihood, and that optimal Q is a posterior distribution. And then while fixing this Q as that posterior distribution, and we update our data again. Okay, so these are the parameters that we have over here. Okay, the green marked, green highlighted values are updated, and then based on this updated or changed values, we newly obtain the posterior distribution and set it as our new Q. Okay, so this is an overall process of this EM algorithm, and from this perspective, it can be viewed as like coordinate ascent. So whether it is an ascent or descent, it is not important. Yeah, but we are maximizing this measure, and we studied or discussed about this coordinate descent or block coordinate descent, right? So if we have maybe 10 different variables, and then we set maybe 2 of them, and then optimize the rest of 8 variables, and then we optimize this 8 variables and then set their optimal values, and then treating them as a constant, and then we update the first 2 variables once again, and then we iterate through these 2 processes, right? So in this sense, we now have these two sets of variables to participate in our optimization process, where the first one is data, and then the second one is our Q, which is a posterior distribution. Any questions so far? Okay, and then let's take a break for 10 minutes, and then I will go through some of these Gaussian examples based on this EM algorithm.
그럼 지금까지 이스트에 관련해서 그 세타랑 고정되어 있을 때 Q가 어떻게 최적의 Q가 어떻게 설정되어야 되는지를 설명을 한 거잖아요. 네. 그러면은 방금 전에 말했던 이제 이 코어디네이트 어센트라는 이쪽 부분이 이제 세타를 어떻게 찾을 것인가를 하는 부분인데.
이거요?
네.
이거는 그러니까 이제 Q랑 세타랑 둘 다를 찾는 지금 과정인데.
그렇죠.
네. 그러니까 Q를 찾는 거는 아까 포스티리어로 유도를 했으니까. 네, 맞죠. 그게 우리 옵티멀 Q가 되는 것이고, 네. 이제 그 Q를 설정을 했을 때 세타를 또 이렇게 다시 한번 찾는 과정을 또 하죠.
네. 근데 그때 찾을 때 지금 그 코어디네이트 어센트를 사용한다는 건가요?
네네네. 그 코어디네이트 어센트라고 볼 수 있는 이유가 이제 뭐냐면, 이제 Q는 Q대로 아까 이제 여기서 이게 괜히 좀 약간 컨티뉴어스 랜덤 베리어블이라서 좀 설명이 좀 어려웠을지 모르겠지만, 이 가우시안 믹스처 모델로 생각하면 Z는 결국은 1, 2, 3의 세 가지 값을 가지는 이제 멀티 논리 디스트리뷰션이잖아요. 그러면 이 같은 도메인 혹은 같은 인풋 밸류에 대해서 정의될 수 있는 어떤 arbitrary한 probability distribution을 우리는 생각할 수가 있고, 그게 Q라고 생각한다면 원래 Z가 따르는 뭔가가 있는데, 그쵸. 이제 1, 2, 3에 대해서 또 다르게 이제 정의가 되는 probability distribution이 있고, 그걸 이제 Q라고 설정을 할 수가 있고요. 그 Q를 아무 Q를 써도 이 과정을 만족하셔도 되고, 이것도 만족해요. 네네. 근데 이제 이 Q를 그러면 어떻게 세팅을 하면, 그러니까 Q 자체를 우리의 이제 그 옵티마이제이션에 이제 참여하는 그 변수로 볼 수가 있어요. 어떻게 볼 수 있냐면, Q는 기본적으로 이제 요거 두 개의 변수, 그러니까 Z가 1일 때 2일 때 각각의 확률값, 그리고 그것들은 이제 0에서 1 사이가 되고, 이제 썸이 1은 되면 1보다는 작거나 같고, 이 마지막 거는 이제 디그리 오브 프리덤 측면에서 이제 첫 번째 두 번째 거를 결정하면 마지막으로 얘는 알아서 결정이 되는 거니까 얘는 뺄 수 있고요. 그러면 여기서도 이제 Q 오브 Z를 이제 디파인 하기 위해서의 베리어블은 총 2개가 있는 것으로 볼 수가 있잖아요. 그쵸. 네, 그러니까 이거 2개도 우리의 변수로 보는 거예요. 세타 같은 여기서의 요 변수도 요것도 우리의 변수로 보듯이, 이 QZ에 이제 이거를 디파인하는 그 각각의 파라미터 밸류 자체도 우리의 변수로 보는 거예요. 그렇게 되면 별다른 이제 큰 특성에서의 별다른 차이가 없이 어떤 전체적인 베리어블이 있고, 그 중에 이제 요만큼을 먼저 업데이트하고 저만큼을 나중에 이렇게 번갈아서 산다는 거죠.
알겠습니다.
네.
이렇게 좀 전반적으로
네.
어떤
네.
그 결국에는 이제 그 EM 알고리즘이라는 게 옵티마이제이션 시켜준 다음에 그다음 맥시마이즈 시켜서 계속 그걸 번갈아가면서 이제 진행하는 건데 처음에 이제 제가 이해가 안 됐던 게 그 로그 여기서 시그마에서 로그가 시그마가 밖으로 빠지는 부분에 대해서 잘 이해가 안 돼가지고요.
네네네.
그래서 이게 어떻게 이렇게 빠질 수 있는 거예요?
이게 로그가 이 안쪽으로 들어가는 거요.
예.
그러니까 그게 이제 아까 그 어떤 젠슨스 이니퀄리티에서 지금 요 지금 핑크색으로 친 박스는 결국은 이 매저가 있을 때에 얘에 대한 어떤 컨벡스 컨비네이션이에요. 왜냐하면 QI가 이게 디스트리뷰션이기 때문에 디스트리뷰션이 곧 이제 컨벡스 컨비네이션의 코에피션트로 쓰일 수가 있기 때문에 그래요. 네. 그럼 이만큼의 이제 그 컨벡스 컨비네이션이고요. 컨벡스 컨비네이션 먼저 해줬죠. 그 다음에 로그 펑션을 취했어요. 근데 로그는 이제 컨케이브 펑션이기 때문에 이 컨벡스 컨비네이션을 나중으로 빼는 거예요. 로그를 먼저 하고. 그러면 이게
프로젝트 문의드리려고 그러는데 그 주제가 예를 들어 뭐 새로운 또 논문 이런 거 말고 예를 들면 지금 배운 내용을
꼭 새로운 거는 아니어도 돼요.
뭐 배운 내용을 어떤 데이터에 다 적용해서 뭐 시뮬레이터를 한다는 뭐 이런 종류도 괜찮나요?
네, 그래도 괜찮아요. 네.
뭐 언어는 뭐 특별하게 어떤 걸?
언어는 뭐 파이썬을 권장하지만 뭐 꼭 그렇지 않아도 될 것 같아요. 네.
주제가 뭐 논문이랑 새로운 거 아니더라도 배운 거 적용한다 이렇게 해도 괜찮은 거예요?
맞아요. 네. 꼭 새로운 건 아니어도 돼요. 네.
그 기말고사랑 탐 프로젝트랑 같이 있는 건가요? 아니면 따로?
그렇죠. 같이 있죠.
아 그러면 그 탐 프로젝트와 기말고사 대체인 건가요?
두 개를 다 같이 본다고요.
그러니까 기말고사도 보고 탐 프로젝트도 보는 거죠? 탐 프로젝트는 그냥 준비하고 있는 것들 이제 뭔가 레이트 형식으로 내면 되는 거죠?
그렇죠. 네, 맞아요.
알겠습니다.
네. 세이버.
수업 시간 질문 드리려는데 화장실
네.
그 여기서 그러니까 다른 건 다 이해되는데 C가 왜 이제 컨스탄트예요?
C가 컨스턴트해야 되는 이유는 그러니까 이제 젠슨스 이니퀄리티가 이제 이게 저기 등식이 되려면
그 앞에 조건이 있잖아요.
네. 네네. 이게 등식은 그냥 요 x가 그냥 랜덤 베리어블인데 그냥 x가 그냥 컨스턴트일 때라는 뜻이에요. 그러니까 이제 이 펑션에 들어가는 x들이 여러 개의 값을 가지고 그것들에 대한 뭔가 컨벡스 컨비네이션 우리는 생각을 하잖아요. 근데 그게 그러면 안 되고 그게 그냥 하나의 값으로 모아져서 그러면 이제 내분점도 그렇고 걔네들 각각의 포인트들이 그냥 다 똑같은 포인트일 때에 그러니까 이제 여기서도 이제 만약에 두 점이 똑같은 점으로 주어져 있으면 그러면 내분점도 그 똑같은 점이잖아요. 그렇기 때문에 그것에 대한 펑션 밸류를 그러니까 먼저 내분점을 취해도 그 점이고 그러니까 이제 그것에 대해서 이제 펑션 밸류랑 그것을 먼저 펑션 밸류를 한 다음에 그것도 펑션 밸류 똑같은 거를 또 내분점을 해봐야 또 똑같잖아요. 그렇기 때문에 결국은 요 x라는 값이 그냥 컨스턴트 값, 그러니까 이제 실제로 이제 랜덤 베리어블의 관점에서는 이 값, 저 값 다양하게 될 수가 있어서 그 각각의 이제 확률 값들이 이렇게 있는 형태가 우리가 일반적으로 생각하는 랜덤 베리어블인데 그렇지 않고 x 값을 그냥 하나만 가지는 그냥 값이라는 거예요.
그렇게 되면 이제 그 컨벡스든 컨케이브든 이제 그 등식이 성립을 하니까 그래서 이제
그래서 여기서 x라는 역할을 하는 게 여기서의 그렇죠.
그래서 얘를 이제 컨스턴트 놓고 이 식으로 정리해서 이제 q가 이제 이렇게 되는 거죠.
맞아요.
감사합니다.
연구실은 안 계셨는데 연구실은 조정대 이렇게 나오거든요. 그죠? 정신적
All right, let's continue. Okay, so from this perspective of a coordinate descent or coordinate ascent or block coordinate ascent, yeah, I think it is a little bit, I mean, relatively easier to understand. But yeah, I think, yeah, it will be kind of desirable, or it will be recommended to understand really deeply about all these stories. Okay, because that is a really fundamental kind of theory for many of these yeah, probabilistic generative models. Okay, so LDA or linear latent Dirichlet allocation or variation autoencoder. And there are so many probabilistic generative models, and that is all based on this EM algorithm. Yeah, so it is really important kind of theory. Okay, so yeah, looking at this guy. So initially, is this our log likelihood? Is this log likelihood? It is not, right? So if this guy was put inside, and then it will be our, yeah, it will be our log likelihood. But this guy becomes equality when Q is set as the posterior distribution, right? And then we update theta once again, so that we just yeah, we just maximize this representation, right? Because that representation is still our yeah, our our lower bound. Okay, so given this lower bound, we can just update our parameter theta so that we can also, yeah, improve this lower bound quantity. Okay, and then once again that will become this guy strictly positive. I mean strictly kind of strict inequality over here, and then we make them as an equality by just adjusting QI's once again, and so on. Okay, so this is the overall process, and then let's look at the example by using Gaussian mixture model, right? So in this case of a Gaussian mixture model, what is our Z? Z is this guy, multinodal distribution. Okay, so we have to choose Z as some arbitrarily chosen distribution. So we don't know these values yet, right? But they will have their own kind of parameters, although we don't know. But we can consider the distribution of Z that can be used as a QI of ZI as maybe 1, 2, 3, and then we can think of this kind of distribution of 0.2, 0.6, 0.7, and 0.1, for example, and so on, right? So we can think of this kind of arbitrary distribution as Q, but we have to choose Q as our posterior distribution. Like this. Okay, so let's see how we can compute this. Okay, so so let's consider this weight as, for example, 1, 2, 3, and our QZ as so this value as WJ. Okay, so if it's a 0.2 for Z1 and W1 and for the first data item, and then it will be 0.2 and W2 sorry, 0.7 and 0.1, and then 0.7 and W3 as 1 for the first data item is 0.1. Okay, so this can be viewed as our Q. Okay, but these values are determined based on this posterior distribution. So this posterior distribution has a lot of parameters. So this is pi or P. 이거 파인가요? 파? 맨날 헷갈리네 이거. P? P요? P? P? PHI? P죠 그러면 Phi. 맞아. 이거를 이제 파이라고 읽고, 그렇죠. 이거를 이제 Phi라고 읽죠. Phi. Right. Great. Yeah, this is Phi. And what is Phi? Phi. We need this guy. 슬라이드가 아니 공간이 없네요. Okay, so these parameters are phi. Okay. Okay, so here the posterior distribution is defined in this manner, and then let's see. Yeah, it is not showing the detailed expression, but how can we obtain this? So here the main point is, so we are using the currently set or currently estimated parameters. So suppose these are the parameters, and let's suppose x is also x is just a scalar. So it's maybe 170, and maybe this guy is 5 squared, and this guy is 185, and this guy is 10 squared, and we can think of this third one, right? And then suppose x1, okay, x1 is 160, 178, for example. Okay, and then we can consider this x being 178 where z is equal to 1, or yeah, let's consider this joint density. So in this case we have to follow this route where z is set as 1. So what is the probability of choosing z as 1? It is this guy, 0.2. 0.2 times the probability. Yeah, so from here, 어떻게 x being 178, where 어떻게 where x follows this. 모르겠네요. 170 and 5 squared. Okay. Okay, so p 178 and z is equal to 2. Okay, so we can similarly obtain or compute the probability as 0.7 times p of x being 178, where this guy is following 185 and 10 squared, and we can obtain p of x being 178 where z is equal to 3, right? So are there any variables over here? So there is no variables because we also we just used the currently estimated value for phi and mu and sigma. Okay, and then for xi is always given, so this is an observed variable, and so we can obtain each of these 3 cases. And then suppose this guy is 0.02, and suppose this guy is 0.05, and this guy is 0.01. Okay, and in this case, what is our posterior probability? So this, what is this? So this is this is the joint distribution or joint probability distribution of xi, x1 or and z1, this guy, right? And this these 3 values are like z are z can have a different values, so z are inputs, right? But x is fixed as 178 because x is always fixed as our observed variable. Okay, so this is like the sectional image or the sectional graph from this joint distribution, right? And x is fixed as 178, and z1 and z2 and z3, which are the 3 possible values of z, and then we computed their joint probability value of these 3 values, right? And then what should be our q in this case? Q is just their posterior distribution, right? So 이거 어디 갔죠? 이거 지워졌지? 이거 왜 지워졌죠? 다시 돌아갈 수도 없고. Okay. Right, so this is a QZ, and this QZ is like, so this guy should be set as 0.02 divided by 0.02 plus 0.07 plus 0.01, right? So that way we can fix or we can assign the first variable that specifies our Q, right? Because that is the posterior distribution or posterior probability assigned to z is z as 1. Okay, and then we can just change this guy as 0.7, the 7 and the 1, and that way we can obtain each of these values that will form our Q. Okay, So that's how we obtain or compute this posterior distribution that will make this Jensen's inequality to be equality over here. Okay. All right. And then once we determine Q as a particular distribution, so in this case, if we started from all known values of our parameters of phi and mu and sigma, which are kind of currently estimated values. Okay, so these are known values, and based on these known values, we updated or we obtained the optimal Q, right? And then it's time to plug in this optimal Q into this expression. But which expression to use? We have to use this expression, because these are now holding the equality, and so we will utilize this expression, and then we will also improve or maximize this guy with respect to our theta. So now instead of using fixed theta, we now view our theta as a variable, but z is, or this q is fixed as our posterior distribution. So q is now known, but we now treat our parameter theta as our variables. Okay, and then now we update our theta. And what is our theta? Theta are these ones, right? Okay, so so using this q as this optimal representation, and then suppose that values as this guy. Okay, so these are just the known values that we we showed over here. Okay, so these w's are just fixed known values, and then from here, we can just plug in these w's as our optimal choice of q, and then this joint density is represented in this form, and divided by this, and this guy is w. Okay, so we don't need to worry about this w, because w is just a constant value that we already obtained from the previous step, right? Okay, and then now we obtained this complicated expression, which correspond to like this part, right? This part, and then it's time to optimize this expression with respect to our parameters of phi and mu and sigma squared. Or in the case of multivariate ones, it will be the matrix sigma, right? And then how we do it? We just perform the partial derivative with respect to phi and also mu and sigma squared, or this matrix sigma. Okay. So given this representation, for each of these mu1 and mu2 and mu3, so we just compute their partial derivative given this complicated expression. But many terms are not related to mu1, and so we can just ignore them, and then we can only consider those terms involving this mu1. And then once we perform this some derivations, okay, and then we obtain this, and then it should be set as 0. So it is not like a gradient descent, right? So we need to obtain the optimal solution from the perspective of coordinate descent or block coordinate descent, right? So we obtain this expression for the partial gradient with respect to w1 and w2 and so on, and then set it as 0, and then w is obtained in this form. Okay, and then we can do the same thing on sigma L or sigma 1, 2, and 3, and also this phi, okay, which is our prior. Okay, And okay, so yeah, I think that's all I want. Yeah, I want to say about the derivation of this EM. So yeah, any questions so far? Okay, so yeah, we omitted a lot of the derivations, especially for this partial derivatives with respect to each of our variables, and also in the case of phi. So even if yeah, even though phi, I mean, even though it looks like having these three variables to specify over here. Yeah. Even though we have three variables to specify our prior distribution for Z, which is a multi-nonlinear distribution, but in this case, yeah, they should sum up to 1, right? So in terms of the degree of freedom, the degree of freedom is only the 2. So in that case, we can represent these parameters as yeah, this one as a maybe phi1 and phi2, and this guy as a 1 minus phi1 and 1 minus phi1 minus phi2, or we can just set this guy as phi1, phi2, and phi3, and then they phi1 plus phi2 and plus phi3 should be equal to 1, right? So we have this kind of constraint given these three variables to optimize, right? So in this case, yeah, involving this or this solving this constrained version of the optimization problem, yeah, we can use this Lagrange multipliers like this. So yeah, all the sum of phis should be equal to 1, and so yeah, -1 should remain as 0, and so this one should be always 0, and so even if we add it to our original objective function, it will not influence at all, or it will not affect at all, and so we can have this kind of unconstrained version. And then if we set it as 0, I mean if it's a gradient is set as 0, and then we can obtain the solution for our optimal phis for phi1, phi2, and phi3. So that is how we update our yeah, our parameters, phis as well. Okay, so let's get back to our material. So at least we know how, yeah, we understood how we set our Q, right? Or Q is parameterized by W, or in this case W, K, and I, right? So yeah, following the notation from the previous lecture slide. So this is the posterior of Z being K, right? For the data item I, right? And then in this case, yeah, these are like W, yeah, W1, 1, and W2, 1, W3, 1, and so on, right? So we can obtain this posterior distribution at a particular parameters that we currently have, right? And then these are WIK over here, and then yeah, these are the posterior expression, or mathematical expressions to obtain this posterior distribution. And then you can see that this guy is exactly the same as what we did over here. So we just first compute. Yeah, so yeah, intuitively our x, which is 178, can be generated from Z1, C1 being Z being 1, and Z being 2, and Z being 3, right? So we have like these three paths, right, of generating 178, right? So we have these 3 passes, and then compute the probability of each pass, and then just normalizing them. So that's the meaning of our posterior distribution. Okay. And again, this is closely related to LDA. Okay. So computing this posterior distribution is assuming a fixed or particular parameter values of alpha and mu and sigma, right? So in the case of LDA, in the case of an LDA, let's see. Okay, so so in the case of an LDA, we assume the common covariance, right? But in the case of Gaussian mixture model, we assume different covariance matrix and different means, of course, right? So let's imagine we have 3 different mountains that have their own kind of shape of this covariance, right? And then given a particular x point or data item x, maybe over here, right? And then, yeah, each of these mountains will be scaled by our prior. So if it has a prior of 0.2, 0.7, and 0.1, and then it will be scaled down by factor of 0.2, down by 0.7, down by 0.1, right? So that's how we adjust this mountain's height for each of these mountains by reflecting the prior, right? And then for a given point of 178, for example, or one particular observed data point, and then we evaluate the height of each mountain, right? Height of each mountain. Okay, so that height of each mountain is these values, right? And then we just normalize in a way that their sum is equal to 1, right? So that's how we obtain the posterior distribution at a particular x value. Okay, right, having that in mind, given a particular Gaussian Gaussian mixture model having a particular prior and particular mean and variance for each Gaussian, okay, and then we will have an x1 and its posterior distribution, okay, and then x2 as its own posterior distribution, right? So we are given a fixed mountain scaled by its own prior, and suppose our x1 is over here, and then we obtain the height of each mountains and then normalize it so that the sum is equal to 1, and then suppose x2 is over here, and then we also evaluate the height of each mountain at this particular point, and then normalize it so that their sum is equal to 1, right? So for each of data point, and then we can consider posterior distribution, right? And then posterior distribution will all be defined for the 3 discrete value of 1, 2, and 3, right? 1, 2, and 3. So you can imagine like this kind of table. So the given a particular phi and mu i's and sigma i's, okay? In this case, suppose our data item 1 and this is C and 1, 2, and 3. Suppose the posterior probability for this x1 is like 20% and 70% and 10%, and for x2 and maybe 90% and 8% and 2% and so on. Okay, then this guy, let's consider it's a 2-dimensional kind of version, and this 2-dimensional version is like 170 and 75 kilogram in centimeter, okay, and this guy and 185 and 60 kilogram, okay, for a given Gaussian mixture model parameters, we can compute all these posterior probability values, right? Okay, so we know how we obtain these probabilities, right? And then now after kind of deriving the gradient set as 0 and then obtaining the optimal solution for alpha or phi over here, and mu and the sigma. Okay, so let's consider, or let's look at these expressions. So these are the final derivation result once we just compute or write the gradient expression with respect to a partial or a single particular variable of this guy, and this guy, and then set it as 0, and then these are the optimal kind of derivation expression or representation. And then here these expressions are something like this. So this alpha is alpha is obtained in the following manner. Suppose we have a 10 different data points. Okay, we only have a 10 different points. Okay, so suppose we compute this posterior table. Okay, and then what will be the sum of all these tables? Each row will sum up to 1, and we have 10 points. Okay, so each table, I mean the sum of all the elements will sum up to 10, right? And then so that 10 is just equal to the number of data items, right? And then now this guy, okay, let's just sum up the first column. Okay, and that will be our phi1, or prior distribution assigned to the z value of 1. Okay, so that is this expression. Okay, so even if nk is looking like an integer, but nk is just a posterior distribution that we see over here in this table. Okay, so this guy, summing up all of these posterior probability values and dividing it by 10, or the number of total number of data items, and then that will be our new prior probability, I mean optimal probability for our prior distribution. And likewise, yep, we do the same thing by summing up the second column, and that will be, okay, the second one. So that will form these values, 0.2, 0.7, and 0.1. Okay, so what does that mean? Overall, from this posterior distribution, we consider overall how many points are like belonging to the first Z component, or Z1, and Z being 1, and Z being 2, and Z being 3. Okay. So in this case, let's consider the linear discriminant analysis. So what's the difference from the linear discriminant analysis in the case of Gaussian mixture model? So when studying the LDA, we didn't need to suffer from this EM algorithm and this kind of Z stuff, because in the case of an LDA, it is basically a supervised learning setting where each data item has the class labels. So if we consider the three class classification problem, and then our first data item is belonging to, for example, the second class, and then we can consider this kind of posterior probability table as fixed constant, where we have a one hot vector for each row as 0, 1, 0, and the second one, maybe the second item is belonging to the third class, and 0, 0, 1, for example. Okay, so in this case, we still need to estimate, I mean, in the case of an LDA, we still need to estimate the prior probability and also the likelihood, parameters of mu and sigma squared, right? And so what is our optimal kind of parameter estimate of Gaussian mixture model? If you guys remember, like this guy. The prior probability and its parameters are optimally estimated as the ratio of our data item out of the entire data item, right? So that was our derivation result of an optimal estimate of the prior distribution, right? So this is almost the same over here, but here we are not given a fixed kind of table where we have a particular data item belonging to completely to a single class or single component, right? So this table is now like a soft kind of membership. So this guy currently this x1 is belonging to the first component with the 20% probability and the 70 and the 10% probability, right? Because these are not known values, so we have to estimate this class probability of each data item in this manner, in the form of posterior distribution. Okay, but still, given these as a fixed values, and then the rest of the story will almost be the same. Okay, so here, this guy is still the same, right? Except that our class membership is now possibly this kind of soft membership vector instead of a one-up vector. Okay, and then also the rest of the stories are the same. So how did we estimate like mu and the sigma for each component's Gaussian? So so we just collect, or we just choose those data items belonging to the first component or first class, and then only using them, or only using this subset of our data items, and then we estimated this mean and estimated this variance, right? So this notion is now becoming or relaxed or extended by using this soft membership. Okay, soft membership. It's almost the same, but here the only difference is this nk is this nk is okay. So let me just give an intuition. So from here, so if we had a one-up vector of 1, 0, 0 and 0, 1, 0, 0, 0, 1 and maybe 1, 0, 0, and then we just collect these two, and then just estimate their mean value by using only these two, right? But here we have a soft membership probability, and so here, so we have 20% over here, and so we just multiply by 20, and for this guy it has a 90% of a membership, right? So 0.9. Okay, and then once we compute this weighted sum, and then we perform or convert it into weighted average. So if it is a 20% and contributing with the 20% and the 90%, and then if we just only consider these two, and then we just divide it by 1.1, so that we can perform this weighted average. Okay, so this nk is what? The column sum. Okay, the column sum, or the sum of all the weights, and the this covariance matrix, or the variance, is also similarly computed. So we have a weighted weight value, and so we obtain this x nu, I mean this mean vector that we newly updated, and then compute their covariance value contributed by the first data item and the second data item, and then we assign their weight with respect to this posterior membership, and then divided by the total membership assigned to the first class and the second class and so on, so that we can perform the weighted average. So in this sense, it is almost the same as this guy, but we now use the soft version of this latent linear discriminant analysis kind of thing. Okay, so that is the Gaussian mixture models and how we derive it. And then once we obtained or updated phi and mu and sigma, and then we go back and then we compute the posterior distribution, and then we now update this entire table based on the newly updated parameters of phi, mu, and sigma. And then we do the same thing of updating phi, mu, and sigma based on this newly updated posterior table, and so on. Okay, any questions so far? Okay, so in practice, how we perform this EM algorithm or this Gaussian mixture model fitting given a set of data, we just initialize, or we randomly initialize those values, mean and the sigma and the prior distribution. We just randomly initialize them, and then we can now obtain the posterior distribution, and then using it we can now newly update our parameters. Okay. Okay, then so this is the example of the Gaussian EM algorithm iterative process. And so here we can see that like this, the centroid or the mean of the two Gaussians are initialized as these 2 points, and then here we can see that the covariance is just a diagonal one, right? And then from here we perform this, right? So what's the meaning of this figure? So this meaning, I mean the meaning of this figure is representing the posterior. Okay, so yeah, in the case of k-means, I mean it's almost similar to k-means, and k-means can also be viewed as a special case of this EM algorithm. But anyways, so for this guy, so we can think of their mountain, right? So mountain, and then suppose our prior distribution was just an equal as 0.5 and 0.5, 50-50, and then the mountains will no longer be downscaled at all. And then for each point we estimate or we evaluate the height of the two mountains and then their posterior distribution, right? So in this case, it's like those two are like mixed together with each other as maybe 70% and the 30% and so on with respect to their height of these two mountains. Okay, and then using this we update their new mean and the covariance, right? So here roughly those are contributing to update or determine the new mean and the covariance, and thus we now obtain this guy, center point over here, center point over here, and so over here we obtain this, right? And then we go on, and then we obtain kind of this kind of final result, where the first Gaussian is like this and the second Gaussian is shown in this form. Any questions? Okay, and then let's discuss briefly about the practical issue of this Gaussian mixture model. And then it's requiring the the number of components should be initially set, right? And also sometimes this EM algorithm is prone to this local minima or bad local minima, and sometimes one of the exemplary bad local minima is shown as this singularities, as we will see in the later slide. And so in this case, if we use 4 Gaussian components, and then yeah, we can have these 3 components, but there is a 4th component that is not used at all. Okay, so suppose in this case we start with the 4 number of Gaussian components, but somehow when computing this posterior table, and if we have 4 over here, and then their probability are computed as all zeros. So in this case, yeah, in this case, yeah, there, yeah, we will just, it will be like practically using only the 3 components in this case. So we can see this kind of, yeah, Gaussian components that are not hardly used at all. And then also if we use the too few or too small number of Gaussian components, and then we have this kind of, yeah, result. And then also we can see some singularity problems. Let's see. So I'm going to just briefly mention about the singularity problem. So when running this Gaussian mixture, I mean EM algorithms to fit our Gaussian mixture models, when starting with the bad random initialization, and then sometimes our Gaussian, yeah, one of our Gaussian component is just relying on a single data. Okay, single data. So suppose this guy is like somehow our posterior table is like so this is the 3rd component, and then z1 0 0 and so on, and maybe somewhere over here z7 is 0 0 1, for example. Okay, and also 0 and so on. Okay, so in this case our Gaussian, I mean their mean and the variance will rely on only on single data item. Okay, so in this case, what will be the mean value? So so this is an x1 and x7. So this is the coordinate of x7, right? So we typically use it, write it as this one, right? So in the case of an x7, what will be its optimal parameter for mean? Because we have no other contributions over here, right? And the only 1 data items are contributing to this Gaussian, and then the mean value will be easily determined as that point itself, right? But what about the covariance? Covariance can be problematic because in this case covariance is now, yeah, okay, so before thinking of this covariance matrix, let's just think of scalar kind of case, I mean univariate case. So x is 178, for example. So in this case, using the single component, and then fitting the Gaussian, the mean will be 178, of course. And then what about the sigma squared or variance? Variance will become 0, right? Because 178 minus the mean, which is 178, will become 0, right? And so in this case, when thinking of the Gaussian 178, and then we can think of this general kind of pattern or general shape of a Gaussian PDF graph. But in this case, it's like this kind of delta function. Okay, so this Gaussian distribution is really like this delta function, where we have infinitely large value at this point of 178, but zeros at all the other x values, right? Right. In this case, let's re-evaluate the posterior table as well. So for this guy, for all the other guys, let's consider the mountain, the height of this corresponding mountain having this kind of a really sharp shape. I mean, if it is different from 178, then what is the height of this Gaussian mountain? It will be just a 0, right? Just a 0. And then all the other mountains will have some height, right? And then can you imagine the next stage of a posterior table? This guy, yeah, for all the other guys, will still have 0 components or 0 class or 0 component memberships, right? Because that is differently located from this this x7, right? And thus in the next stage there is no opportunities for other points to influence or contribute to update the parameters of this Gaussian, right? And then what about this guy? Okay, in this case, this guy will have infinitely large density value, right? Infinitely large density value, and yeah, it will have some height coming from the other mountains, from other Gaussians, right? But if we consider their relative posterior distributions, and then this guy is an infinitely large density value, right? And then all the other values from other mountains will have some finite probability values, and thus it will just remain as 0, 0, and 1. Okay, so it's like a deadlock, or it's like yeah, it can be viewed as like bad local minima. Okay, so we don't want this kind of result where our Gaussian component is just relying on a single data point. So that is the issue of this singularity stuff. Any questions? Okay. Okay, and then let's get back to a little bit higher level and compare k-means and the Gaussian mixture model. And as you guys saw in our midterm exams, so you guys have to understand well about the difference of k-means from the Gaussian mixture model and so on. Okay, so in the case of a k-means, okay, in the k-means, so let's look at this iterative process of EM algorithms to fit our Gaussian mixture model. Okay, so in this case, so if we were to perform the k-means algorithm, and then we will just draw this this perpendicular line and with an equidistance with these two centroid points, right? And then these points will be assigned to either one of them, right? And in this case, we can also consider this process of having this class membership or cluster membership probability as being one hot vector, right? One hot vector. And then let's imagine this kind of process. Okay, so in this case, in the case of k-means, okay, so let's just let me just try to make this process let me just try to simplify this process to make this equivalent to k-means. Okay, so let's skip this part, the prior part. So prior is always assumed to be equal probability. In the case of two classes, 0.5 and 0.5, and in the case of three clusters, and then one third and one third and one third. Okay, so we can consider that this prior distribution is fixed as uniform distribution. Okay, and then now let's think of this guy. Okay, this guy. Okay, this guy is like, yeah, since we are allowing only the hard membership, right? So one of, yeah, each data item should belong to should belong completely to one of our component, right? 100 and 010 and so on. So that way k-means can be viewed as having hard cluster membership, right? So once we assume that our cluster membership probability as this one hot vectors, and then this guy, okay, the way of updating centroid will be the same. Okay, we just compute the centroid of these member points, right? And then now, what about this guy? This guy. So in the case of k-means, we also skip this part. We skip the first part, and also we skip the second part. And if we still want to view the k-means as a special case of a Gaussian mixture model, and then, yeah, again, we are maintaining the uniform probability for prior, and also in the case of this guy, we can consider it as like having having the covariance matrix as an identity matrix, which means like this guy. Okay, so let me show how we can understand this process as a k-means. Okay, so here, yeah, initially, yeah, we need a, yeah, suppose, yeah, we start with this randomly initialized two Gaussian components, and then we also have a randomly initialized prior distribution, and then we would have a scaled it properly, right? Maybe if it is assigned with the 0.7 and the 0.3, then this one will be much strongly scaled down, right? And then after this scaled version of these two mountains, we will evaluate for each point's height of these two mountains, right? But in the case of k-means, we just assign the same probability, which means we have no scaling process at all. And we have two mountains, and two mountains will always have the unit, the identity covariance matrix, and thus these two mountains will always be spherical, and their radius of this mountain will always be the same. Okay, so basically the shape of these two mountains are the same, okay, and they are spherical. Okay, so in this case, for each point, we just compare the height of these two mountains, right? And the height of these two mountains, and then we just choose the mountain that has the larger height. Okay, and then we just completely assign that guy into that component. Okay. Okay, and then here, so now these guys, so these memberships will be either 10 and 01, right? Because we are considering the hard membership in the case of k-means, right? And then now we are also updating the prior distribution with respect to the, yeah, as the sum of each columns, right? To reflect the how many number of data items are assigned currently to a particular component. Okay, so if the first component gets assigned for many of the data items, and then it will have, accordingly, it will have larger prior probability, right? But we are just skipping that part, and then we just still fix the prior distribution as 0.5 for each Gaussian component, and we updated mean as over here, but here we also maintain the covariance as the spherical, like this, or so these two are still the same mountain, Okay, we are not using this mountain, which has this updated covariance patterns or covariance characteristic. We just stick to this spherical mountain that have the same radius. Okay, and then again the prior distribution is still remaining as the same as a uniform distribution, so there is no scaling. Okay, and then given these two mountains for each data item, yeah, we just compute their mountains height, two mountains height, and then decide or determine which mountains has the highest one, and then we assign it completely to that component. Okay, so this can be viewed as a k-means process, k-means iterative process from the perspective of this EM algorithm or Gaussian mixture model. Any questions so far? Right, so here, let me explain a little bit more on this the computing the mountains height for this spherical stuff, spherical mountain or spherical Gaussian. Okay, so you guys know how to compute these, right? So here, when computing these three values to obtain the posterior distribution. So here in this case, if we just use a hard cluster membership, and then we will just perform the argmax, right? So this guy has the largest value, so we will just completely assign this data item to the second component, right? So that can be viewed as a hard assignment. But here, if we consider this a k-means case, and then what about these? So these prior distributions are assumed to be equal to each other, right? So we can now just ignore that when evaluating or when determining which mountains has the which mountain is higher at that point. Okay, when computing that, we don't need to consider this prior point, right? And then now, so 178 with respect to this Gaussian and 178 with respect to this Gaussian and so on, right? And then these guys, all the covariances are assumed to be equal, and they are uncorrelated, or they are just spherical Gaussian, right? And in the case of univariate ones, so it's like this. Okay, so I really need to find the space, but yeah, 178 minus 170. I'm just writing the Gaussian PDF expression. So 2 pi, and sigma is always fixed as 1, right? Sigma is fixed as 1, and then exp and minus the squared, and 2 times sigma is what? 1, right? So this is the height of the first mountain, right? And then what about the second mountain? 2 pi times 1, because we assume the same covariance in the exp and the minus and 2 times 1, and 178, which is still our x value, and 185. Right? Okay, so let's imagine another component and its corresponding Gaussian distribution's height. So in this case, when comparing between the three, so we can just ignore this part, okay, and then we still have this exp, and they are having all these exp functions, and then we can get insight to just compare among them, and then we can just remove them or cancel them out because they are all common due to the common or the same covariance. And then what's left? What is left is just a Euclidean distance from the same point or the observed x point x with respect to the first centroid and second centroid and the third centroid and so on, right? So if we consider the height of the mountains that have the spherical covariance, okay, in that case, and along with this same prior probability or uniform prior probability distribution, and then comparing the height of these mountains are boiling down to just computing the Euclidean distance from that particular point to the centroid, or the mean point of each Gaussian. Okay, so that way we can see this process is indeed the same as the k-means process. Okay, so so k-means is based, of course, making the hard decision. So each data point gets assigned to a single cluster, which means a one-hop vector for our cluster membership. And at the same time, this k-means, I mean, from the perspective of a special case of a Gaussian mixture model, this k-means is using the uniform prior distribution, and that uniform distribution is not updated at all. Okay, and also our covariance matrix for each Gaussian component is also fixed as the identity matrix all the time, which is not updated at all. Okay. Any questions so far? Okay, so let me just discuss a little bit more about the physical or intuitive effect of this difference. So for here, so suppose we are given these two Gaussians. So let's get back to just the general form of a Gaussian mixture model where we allow non-uniform prior distribution and also non-identity matrix of a Gaussian covariance matrix. So in this case, let's think of like this point. Okay, so in this case, in the case of k-means, it will be definitely assigned to this red cluster, right? But in this case, we have to consider this a non-spherical shape of a covariant, right? So in this case, our first Gaussian component is saying that along this direction, the rate of decrease, the height decrease of our mountain is not that steep. So it is just slowly decreasing for our mountain's height. So even if this point is relatively having a large distance from this center, because our Gaussian component for this blue one, it has a slow decreasing rate along that direction, and then this point can kind of survive much better. Okay, with in a sense that even if this point may get a larger kind of cluster membership or assignments to this guy compared to this guy. So on the other hand, what about the height pattern or mountain's height of this red one? So red one has also like this direction as the slowest possible kind of decreasing rate of this mountain's height. But what about this direction? So this direction is really steep, right? And so even if it moves a little bit, and then the mountain gets height, it gets really decreasing fast, right? And so even if it is not that far from this point from our Euclidean space, and then this the height of the red mountain may get really small, right? Okay, so so in this sense, we can consider this different Gaussian component and their non-uniform or non-spherical covariance matrix can define our new distance metric. Okay, so new distance. So if we just purely consider the Euclidean distance, and then definitely this guy is much larger than this guy, right? But in this case, we have a different rate of decreasing rate with respect to different mountains that is defined by these two, and then we can think of their distance or similarity based on this non-uniform covariance matrix and this Gaussian distribution. Okay, so this is a one kind of intuitive difference from the k-means that this Gaussian mixture model has. Okay, so but this kind of computing this cluster membership is almost the same as this guy, right? So we also considered like this case where in this case the mountain can be non-uniform. It doesn't need to be spherical in the case of a LDA, but we assumed LDA assumed that for each component they have the same shape of this mountain, right, or the common covariance structure. Okay, but if we relaxed this assumption, and then where is our QDA? So if we have a Gaussian component centered at this point, and then maybe this mountain shape, and for this, and maybe this mountain shape. Okay, so they have two their own mean and also their own covariance matrix. And this LDA, which in this figure they are showing the decision boundary where the height of the two mountains are equal to each other, right? So that is a kind of threshold of like determining whether this guy is assigned to class 1 or class 2 and so on, right? And so in this case, we can imagine like this kind of contour of these mountains, and then I don't know how to draw, but maybe the same the positions or the coordinates that have the same shape, height of the two mountains may have this kind of boundaries, right? So you can think of the Gaussian mixture model as having this kind of curved or quadratic equidistant line. Okay, because Gaussian mixture model by default is assuming different covariance matrix for each Gaussian component, right? But we can still simplify our Gaussian mixture model to have the common covariance and also maybe spherical covariance. And as a related notion, have you heard about the Mahalanobis distance? This Mahalanobis distance is so from here we saw kind of case that these Euclidean distance, or the notion of the distance between the two vectors in a particular high dimensional space, and it is somehow related to some kind of Gaussian distribution, right? And then by default, this Gaussian distribution, if we consider this the distance between this point and this point, and then the difference between the two gets larger and larger, and then this Gaussian PDF value will be smaller and smaller. So distance gets larger, and then the probability gets smaller, right? And then in this case, instead of using, or instead of considering a single Gaussian, multiple Gaussian component, let's just consider first a single Gaussian component, okay, as a simple case. And then you can think of some center and then maybe some Gaussian component like this. So this is specified by our covariance matrix sigma. Okay, and this guy is our mu. Okay, so this mountain is saying that, okay, centered at this point. If we go through this direction, if we follow this direction, and then the mountain's height is really sharply decreasing really fast, but along this direction, yeah, it is not much decreased at all, right? So in this case, let's consider the 2 vector, or maybe 1, 2, and maybe and 2, 5, and then we know how to compute their Euclidean distance, right? And then the Euclidean distance is somehow related to this Gaussian. I mean, yeah, it can be viewed as the exponent, the numerator of this exponent in our Gaussian component, right? And so we can also relate this guy into the notion of this Gaussian component and their height of this mountain. So here in this case, in the case of Mahalanobis distance, we are considering some non-uniform sigma. Okay, and then in this case, yeah, we can either set as this guy as center or that guy as center. So either of them can be set as our center or the mean vector of our Gaussian. Okay, and then let's consider it as mu2. And this guy is our, this guy is a mu, and this is an x and x2, x1. And then mu2 is our, x2 is our mu. And then we can consider their height of this mountain. And then what is the formula for this multivariate case? 1, 2, yeah, x1 minus mu is maybe minus 1 and minus 3. Okay, so x1 minus mu transpose and sigma inverse x1 minus mu, it is divided by 2, right? And the exp and minus and 1 over 2 pi det, something like that. So this is a multivariate Gaussian distribution. And what's the value of it? So center that mu as x2 if x1. So if x1 is over here, okay, so in this case the probability has sharply decreased, right? And then let's consider another one that have the equal distance from the Euclidean distance. They are the same from the same point. But if we have this point, and then this point may have much larger probability value compared to this point, because the decreasing rate is much smaller, right? And so in this case, let's just ignore this part, and then maybe this part. Okay, so this part is really the key or the influencing information that will determine the height of this entire representation, right? Again, the sigma is fixed over here, and sigma is determining the shape of this ellipse. Okay, and then this representation. Okay, this representation. So in this case, in this previous case, so this is almost the same as this guy, right? And this part works. This part is the same as the Euclidean distance, right? And now from this, in this general case of a multivariate Gaussian distribution and their PDF form, and then we can view this part as kind of new version of the Euclidean distance. Okay, so that guy center that u if x1 is following like this direction, and then this value will be much larger with a fast rate. Again, this guy gets decreased very fast, and then it means this part or this part. Okay, this part. This part will become larger with the fast speed, right? So that way, take the negation of it, and then take the exponential function, and then it will decrease sharply, right? And so this distance part is now reflecting our sigma inverse or covariance inverse, and that is like the distance in this warped space. So this guy, this green part, is called Mahalanobis distance. Okay, so in order to use this Mahalanobis distance, we need this covariance to be defined. Okay, but this covariance is defined, and then this guy, similar to kind of Euclidean distance, where so as a special case, if this guy is like identity matrix, it is just the same as Euclidean distance. Okay, so this Mahalanobis distance is also quite widely used in an interesting manner. So okay, so the time's up. So probably that's it for Gaussian mixture. And, yeah, thanks, and let's meet next week. 예, 여보세요? 예, 제가 부재중 전화 받았습니다만은 예. 예, 제가 고려대 주제거리라고 하는데요. 네? 그러세요? 4237-5337 5시 9분에 이제 부재중 전화가 왔었는데요. 예, 뭐 아니시면은 네, 알겠습니다. 예.
I wanted to ask about the project. Like, how does it have to be? Like, can we, in the implementation, can we use other libraries? How we have to implement our own methods?
No, you can freely use the existing or available libraries as well. Yeah.
So it has to be, can be related with anything. For example, my idea is I'm a chemical engineer.
Sure. Yeah.
And I want to use autoencoders to represent molecules. So just like they use languages, for example, when they translate between structures and try to create descriptors, are called, to predict properties.
I see. Yeah, that is possible. So what's the approach or methods to apply to this problem, to your problem? What is your approach?
My approach will be to use, there's two ways of describing molecules that, like, it's a string that represent the structure of the molecule.
Okay.
So both represent the same molecule, but have, like, it's just two different languages. So if I use an autoencoder, kind of in latent space, I think the encoder will have to represent the string in some sort of way to kind of capture the structure.
So you are basically utilizing the autoencoder structure to obtain the meaningful representations? Okay, that sounds good, yeah.
It can be something like that.
Yeah, sure.
Just with these representation results is okay, or should I implement like a further result? For example, predict something in particular, or do a classification?
I mean, in general, it will be good to show the effectiveness of what you did, right?
Compared to other methods.
Right, so just the training autoencoder may not be enough, but you can just evaluate the output of this autoencoder. For example, latent representation in the middle of this encoder and the decoder part. And then you may need to evaluate it based on a particular criteria, I think. I mean, the reconstruction error is just an evaluation criteria for autoencoder itself, but you will probably have trained autoencoder for some other purpose, right?
Exactly.
And so, you can just evaluate that quality of this autoencoder latent vector from the perspective of your main task. And possibly you can have some baseline approaches as well.
Yeah.
So yeah, applying autoencoder and using it, and then maybe we have an accuracy of 85%, and then we can say much about the effectiveness of it. So you can compare it against some baseline methods.
I understand.
Yeah.
That they use normally.
Yeah.
So we are free to use like libraries and stuff like that.
Yeah, of course.
Okay. Thank you.